welcome everybody, and thank you for attending. And it seems quite a long time ago since we started doing these webinar sessions. And as Jennifer said, this will be the last one of this year. And I think we'll all look forward to a new year in 2021, hopefully with some being able to visit and meet people. But what this year has done is has allowed us to begin to do these sort of sessions, and I hope that over the last few months you've found the topics that I've been bringing interesting. So as Jennifer said, today we'll be looking at heavy oil and unconsolidated core. We'll look at really unconsolidated core and the handling of that, but particularly focused on when it's together with heavy oil systems. So I've got a couple of poll questions to start with. And so if Jennifer would like to bring up the first question. So question one is, have you been involved in a study of heavy oil? And then if you have been involved, or you know people being involved, what have you found to be the biggest challenge in those projects?
Give it 10 more seconds, so any last votes? Then I'll end polling. Share the results now.
Okay, so there we have probably roughly 3/4 of attendees today have actually been involved in such a study, either with heavy oil or unconsolidated core. And it seems the biggest problem has been with plug property measurements. Now, there are a number of provisos on that. So I'll show you what we'll be discussing today. Have to just switch back to my presentation. So we'll do a quick recap of why core in the first place, and then we'll look at coring considerations, because although the plug properties and the data from the plug properties may have been the most challenging thing, actually that began when you started coring. And the plug properties may not be a function of the plugs themselves or the measurements themselves. It can be, and I'll look at some of the issues with that, but it really can also stem from the coring and the core handling process as well. So what we'll do is we'll look at those coring considerations, we'll look at well site handling and transport, then we'll look at plugging and plug handling, and then some of the fluid challenges in the laboratory as well. And I'll finish off with a few case studies. I have three case studies that I'll look at, and some of the issues that were discovered with those projects. So the first thing is why core? A lot of people don't, particularly more and more today with higher and higher logs and an AI to try and interpret logs. The past year or couple of years in particular, core has become quite scarce. And a lot of people have started moving towards, say, sidewall cores in the belief that that is cheaper and better. Actually, the cost of taking a sidewall core, if you have to go for 2 runs of sidewall cores, it's probably more expensive than taking a single core. With a single run of sidewall cores, it's probably about the same. But particularly with unconsolidated cores, we can't really take sidewall cores. It's extremely difficult, if not impossible. So at the moment, this is just showing you the value of core. This is look on a 1 mile by 1 mile, that's approximately 1.6 square kilometers of a reservoir, 200 feet or 70 meters thick, and a porosity of 20%. And the oil in place on that, if that was the averages, would be about 8 billion or $7.5 billion at $50 a barrel. The biggest, some of the uncertainties in there, if you had an uncertainty of 1 foot in the thickness, that's about $40 million. And an uncertainty of 1 saturation percent is about $85 million. But the biggest uncertainty is often around porosity, where just 1% porosity change could be almost $400 million of uncertainty in the oil in place. And if we bring that down into things like log properties, the potential errors in seismics is people have said in literature about plus or minus potentially 15% of the length. That calculates into $1.3 billion of uncertainty in that same reservoir. Log porosity is a plus or minus 3.5 porosity units. That's around about $1 billion of uncertainty. And log saturation is 10 saturation units, which is $750 million. And when we bring that down to standard core, then the limits or uncertainty we put around measurements of standard core samples would be half a porosity unit and 3 saturation units. Now, I haven't got data for unconsolidated core and the errors in there, but it will be higher than standard core because it does become a bit more difficult. But generally, we're not going to get or shouldn't get to the same errors that we see in log properties. So we're still reducing the uncertainty usually in core data if the core process has been well handled. And what we'll go through is some of that, the processes and the handling techniques that are going to be required. So what's the first question we have to ask is what's the objective of coring? What are we attempting to get out of it? Is it purely porosity, permeability and saturation in an exploration mode? Or are we looking at appraisal and looking for more electrical properties and log offsets, log calibrations, maybe dynamic properties? Because those change how we will, what fluids we might use in the coring mud, etc. So these should be asked before we start coring. To the sort of objectives you may have: geological, porosity, permeability, hydrocarbon content, which is water saturation. You may be looking for geomechanical properties, or you may be looking at formation damage, particularly if you have sanding issues, and wanting the combination of formation damage and geomechanics to look at well integrity and potential for sanding, or you might be looking at EOR. And before we start coring, we need to consider the objectives, what those objectives are, what measurements we're trying to make, and how are trying to and fit the coring process, the coring equipment, the coring liquids and fluids to match our objectives. So if you want water, for instance, if you want water saturation and you're interested in that, you really don't want to put water into the mud system, because that's going to mix with the more water in the plugs or in my core, and it's going to bring uncertainty into the measurements. So we design coring and core handling to match our objectives, and all of these people need to be involved. And we'll see from one of the case studies that all of these people need to understand why we're doing processes in the way that we're doing them for that particular core. Because if not all of these people are on board with the same objectives and understand why we're doing the procedures, they may begin to use their standard procedures, because the drillers have different objectives themselves. And their objectives is to get the the well drilled and cut as quickly as possible to minimize costs, same as the asset manager. That's going to be, is wanting to minimize costs. But what we're wanting in core is to try and get the best quality core. And so trying to optimize speed with quality. So some of the decisions that we're going to make is the type of equipment we need and what type of core. I've already mentioned sidewall cores are probably not the best for this. So generally going to go for conventional or Y-line, although Y-line gives us thinner or less diameter core, which potentially gives us issues when we're trying to take plugs from that core. So the first thing I would definitely, I would normally recommend this for most core systems, but particularly for unconsolidated core, you want low invasion core bits. So the standard core bit would normally, sorry, I need to put my pointer on again. It seems to have switched off. So a standard core head would normally inject the mud system directly onto the core. And with the viscosity and high viscosities of most muds, that could be damaging to unconsolidated core. That can begin to wash away the core. So we don't want that. So we want a low invasion system where the mud system and the mud fluids are discharged across the face of the cutting surface rather than discharged into the core. That will minimize invasion. It will minimize washing of the core and potential erosion. So those are things that we must consider. We also want to consider the core catcher. So a standard spring-loaded core catcher will not really, is not going to work. The core will just fall out the bottom of the barrel. So we need something to stop that. So this would be, this is one full closure system, a soft catch, where as this is pulled up, these pins pull together and close off. Or you have this hydraulic squeezing of the barrel at the bottom of the barrel, which then holds sand in place, or another clamshell style full closure system, which cuts across. So this was from an SPE paper by Khalid Ahmed of KOC, looking at these different clamshell. This is quite a good paper to read if you're involved in unconsolidated cores. Then we need to consider the barrel, and generally I would suggest the fiberglass plastic barrel. This is more expensive, but there's less friction involved in the core itself. And so it allows the core to move into the barrel more easily. And to slide in. So generally we'd be discussing or recommending this. It also has lower thermal properties. So it's not going to, its size will not change as much as, say, the metallic or aluminium based liners. The one proviso against that is if you think you have a high gas content. So if you have a high gas content in the system, you may want to start thinking about some fluted system that allows the gas to escape around the side of the core. And if you think you're going to have lots of jamming problems, then maybe jam buster. But in general, would tend to recommend the fiberglass. Someone's asked the question regarding low invasion bits. There's a risk of not cooling the core head effectively. What is my take on that issue? Well, thank you, Ugo. It's a good question. Very often, the way that these low invasion coring heads are designed today, they're done together with computational fluid modeling or dynamics to look at the spread of the liquid over the surface of the cutting bit. So they're designed to ensure that you still get good coverage of the cutting bit and get good cooling and lubrication of the bit. So there shouldn't really be an issue there. But yes, it is something just to maybe discuss with the coring company, the design of their coring bit. So outside of the equipment, you also need to consider the process of coring. You really, for unconsolidated core, really need to ensure that you've got full monitoring during coring of your rate of penetration, your weight on bit, the mud rates, the torque in the system, because all of these are going to tell you about potential issues and challenges that you may be meeting as you begin the coring. You want this to be as smooth as possible. Your rate of penetration shouldn't be too quick, because if we're too quick, if we have too much weight on bit and we're pushing through the sediment too quickly, it could be just pushing through rather than cutting. And if we're pushing through, we may not be properly capturing the core. So we want slow coring trips in general, and we want to adjust our core lengths to manage the consolidation of the core. Generally, we need shorter core lengths, say 10 to 20 meter barrels. Barrel types we've already discussed. Mud weight, generally want it to be as matched as possible, so not overly overbalance mud, because that's going to cause issues of erosion potentially. And we want to adjust our well site handling, which we will discuss. One of the things that we want to ensure is that we're not damaging the core. It's essential to understand the potential different damaging mechanisms. The first one here is gas expansion. And you may think, and a lot of people do think, that, well, it's heavy oil, it doesn't have a lot of gas content, but often it still does have some gas content. And particularly for heavy oils, the viscosity of the oil becomes a barrier to that gas, so that it's less able to escape through that viscous system. And so the gas expands and expands, and because you've got soft sediment core, there's a potential that it begins to very easily fracture the core. So yes, we still do need to be careful of gas expansion as we bring to surface. So tripping times is essential. Because it's soft sediment as well, any curvature in the liner from improper handling at surface is potentially going to fracture the core as well. And then other types of damage, this would be from mechanical damage from say a jam, or from, this is a shock pattern from, say, dropping the core or banging the core. So we want to be very careful with this core, because it's soft sediment, it's much easier to fracture and begin to break this core. So we don't want this to happen. We want to model the trip out rates. I'll come on to this one as one of the case studies showing the gas expansion. But how do we model this? So in general, most coring companies, they will have standard rules of thumb of bringing core to surface. So one for liquid hydrocarbon systems and one for gas systems. So the gas system is much slower because there's more gas present. And in the liquid hydrocarbon, where there's less gas present, there's still some gas. So as you get closer and closer to surface, we need to begin to slow down the rate of bringing to surface. And this was first shown in a paper by one of my former colleagues, Isaskun Zubizarreta, in 2011. It's published in the SCA. Basically using computational fluid dynamics to model the trip out rates. So we mesh the core, we apply the core properties to it. That might be the tensile strength, which for unconsolidated cores is going to be even lower than this. It's going to be very low. That tensile strength then limits the pressure or gas pressure that we should allow to be observed inside the core. Because as we bring the core to surface, as we drop the depth, so here's the relation to depth, but also to pressure. So as the outer pressure of the core drops as we bring to surface, and the inner pressure begins to increase because the gas is beginning to expand. It can only come out and move out of the core based on the permeability of the core and the viscosity that it's moving through. And so pressure begins to build up. But in this case, without a mud cake, everything was fine. This was actually a consolidated system. But it's the same process applies for unconsolidated. We put in the critical strength, and then we can, for this particular case with the mud system around, we began to see as we get closer to the surface, we began to see potential problems. The differential pressure exceeds the critical strength. And so that could begin to cause fractures. So what we need to do is optimize our trip out rate. We can go quicker at the start and then begin to slow down at the end. And we can pull to basically the saturation pressure at the quickest that we would allow, and then begin to slow down once we reach that saturation pressure. Once it's at surface, handle the core correctly. Make sure that we keep it and stop it from bending so that we're not fracturing the core like this. And then we want to cut the core into 1 meter sections. Once it's in 1 meter sections, the liner no longer flexes as the liner can do in this instance here. And we can then also stabilize the core. And again, I'll come on and show in the case studies where stabilization is necessary to stop the core from slumping and stop it from moving about in the core liner. And then we want to seal the barrel and or the liner and preserve it and to stop oxidation from atmosphere and stop liquids from evaporating. So as a quick summary, we want to minimize weight on bit. We want to avoid core erosion from high viscosity muds. We want to avoid long barrels because the weight of the core at the top will be pushing down on the lower weight on the lower core and could change the properties. Use full closure systems for capturing the core, avoid liner flexing, avoid shocks, cut into 1 meter sections at surface, stabilize the core, and then CT scan the core when it gets to the lab. So there are other potential considerations about stabilizing the core. Now there are different thoughts here. One is to stabilize with some material around the core so that we're not freezing the core. So freezing has the potential of expanding the water crystals or water into crystals, which can damage clays, it can damage grain-to-grain contacts. So this could be damaging to the core. It can weaken the core even further if it's poorly consolidated. So, and one rule of freezing is the quicker that you can freeze, i.e. the lower the temperature you can apply, and the shorter the distance from the outer to the inner surface of or inner volume, the better. So liquid nitrogen would be the best, but sometimes it would be extremely difficult to get liquid nitrogen to a well site. So one of the things you can do is stabilize the core at the well site, ship it to the laboratory and freeze when plugging at the laboratory. When you're freezing by plugging, the distance around the plug is then is much shorter. You can use liquid nitrogen, which makes the whole freezing process much more efficient. And to stabilize at the reservoir, generally foam or gypsum are used, but gypsum, there's the science or the mixture around that needs to be controlled carefully. So only use experienced laboratories for doing that, or experienced companies. There are issues with foam. So there are hydrocarbon alternatives which have a melting point around about 25 or 30 degrees, or a freezing point, a solidification point around about 25, 30 degrees. Those are alternatives that could be used to solidify around in the annular space around the core and stabilize it. This is just showing you, this is gypsum injection, this is foam injection. And when you're doing foam injection, you have to give expansion points to allow the foam to expand out. Otherwise, the foam will begin to push on the core. And we don't want that, because that's going to damage the core. So we need to be careful. And then we place those meter barrels into a foam-lined container as a shock absorber, sending it back to the lab. And put in a shock monitor, because that's going to tell the transport people that it's being monitored. It makes them more careful. So once it's at the lab, we then have this question: to slab or not to slab first, or to plug or not to plug first. So when we're taking plugs, if we slab through the core, there are two things potentially happening. One, we shorten the potential length of the plug that we take, because we've cut off a portion of the length. But also we've then used another fluid. So what slabbing fluid are you going to use? The best might be air or liquid nitrogen. But again, there are health and safety issues of slabbing with that. It's preferable to do it with a band saw rather than a rotary saw. So there are questions you need to ask about the slabbing if you're going to slab first. But you could plug first, and that might be preferable. So the first thing you should do is take a CT scan so that you can observe the nature of the core inside. You can see fracture points. You can see the stabilization. In this case, it was foam. So you can see where that has worked and stabilized the core. You can also see areas here where it hasn't worked and it hasn't stabilized the core. But this was a slightly more consolidated core, but there's still some fracturing happening. But you also can see more homogeneous systems. And so you can use the CT scans to select homogeneous plugging points or sampling points. You can also see the orientation or the bedding in this. So you can orient the core and take samples in the correct orientation for horizontal and for vertical samples. And then once you've got the orientation, you can either you can bore a hole into the outer layer of the barrel, and then take a plug through that hole in the correct orientation, and then you want to fill or stabilize the hole once you've completed that. So a process might look something like this. The core should remain in the liner. We don't want to take unconsolidated core out of its liner. You perform the core gamma, you then perform CT scan, and you assess orientation and sample selection from that. You then maybe bore through the liner and plug at that location, or you slab and then take plugs. And you take the plugs, but you have to consider what fluid, and that might be liquid nitrogen, it could be formation water, it could be oil. But you want to, once you've taken the plug, you need to stabilize the hole, either with foam or polystyrene dummy plug, or something else, some other material that stops that hole from slumping. So these are then some of the plugging considerations, different types of plugging that might be available. Liquid nitrogen, if you're going to have to freeze the core because it's completely unconsolidated, then liquid nitrogen may have to be used, and freezing may have to be used. Once it's frozen, you have to keep it frozen until you are ready to thaw it in a controlled manner. So if you freeze at the well site, you have to have it frozen and in a container, bringing it to the laboratory and frozen throughout the laboratory until it gets placed into some cleaning process. Plunge plug cutting, you can't use it frozen, obviously. This is just pushing like a coring tool or a corking tool into the core. It's okay for poorly consolidated cores that might be chilled but not frozen, and maybe okay for finer grained material, which minimizes grain movement. But it's one. There's also lathe cutting or milling. Once you've got the frozen core, you could mill down the shape down to a cylinder. Or there are some other specialized plugging systems which have a non-rotating inner barrel and an outer cutting barrel. Once you've taken your plug, you will need to mount the plug. You've got, again, some considerations about what mounting material you might use, either tin or nickel, foil systems, or Teflon heat shrink systems. And this might be based on the planned data you want. If you're looking for electrical properties, you don't want metallic mounting to surrounding the sample, because all your electrical current will just pass around the sample. So then you may have to go for something like a Teflon heat shrink. But this is the process of handling this comes from that same SPE paper. Here's my sample. That you put meshes on the end to stop from grains coming out the end. You apply Teflon tape, which helps to seal between the core and the outer layer, either tin or Teflon or nickel foil. And you also want to try and minimize the amount of material over the end here. You can't get everything away, but you want to try and maximize the area open to flow for that core. And then you need to consider mounting corrections. The weights and the volume of the mounting are going to impact on porosity, and the permeability or the flow resistance of those mesh systems will impact permeability on very high unconsolidated, high perm unconsolidated core. So those need to be considered. And one process for acquiring these would be to mount these, and while they're still frozen, apply a confining stress in a core holder and allow the thawing process to happen with stress in that core holder. And then we're going to need to clean the core, but you need to clean with care. Generally, standard hot soxhlet approach won't succeed or may not succeed. So it's best to do a cleaning study to determine what the best approach will be and determine what the impact of cleaning might be on the core. And for scal, generally the best approach will be to do a miscible injection cleaning. So it's in the core holder, it thaws in the core holder, you keep it in the core holder and do miscible injection cleaning. You then do a miscible injection saturation, so you don't dry the sample. You go straight on into the testing. You may need to estimate porosity by some miscible tracer or dispersion analysis initially, and obtain gas porosity data at the end of testing. And this is how how you design testing and the testing procedures based on what your objective is and based on what type of material you have. And for unconsolidated material, this might be the best approach. You then need to consider how you're going to get porosity. So porosity is potentially, we saw, one of the biggest challenges. It is one of the, in terms of reservoir, understanding reservoir and reservoir uncertainty. It's also one of the big challenges in unconsolidated core. The most accurate measurement that we can make in the lab is grain volume. And the next most accurate is bulk volume by mercury immersion. But you cannot use mercury immersion on very high perm, unconsolidated material, and particularly on mounted material. So we start having to use less accurate techniques. So for Scal, you could use bulk volume by brine saturation, or you could use pore volume by helium expansion into basically similar to the grain volume, Boyle's law expansion into a volume. And looking at the ratio of pressure as the ratio of volume change, and measure the pore volume directly. These would be the best ones potentially to use in this case. What we don't want to do is caliper bulk volume. It assumes a perfect cylinder, and I can guarantee that on these unconsolidated material, you will not have a perfect cylinder. And so onto liquid or fluid challenges. The wax and asphaltene content of heavy oils present issues. They create high density oils. So my heavy oil could be very close to water density, which causes difficulties in separation. It can cause water droplets to be trapped in the crude. So that makes it sometimes errors when we're trying to measure water production coming into, say, crude oil content, heavy crude content, which places errors into our production volumes potentially. We also have the heavy oil droplets sticking to equipment surfaces like glass surfaces or tube surfaces. So we may, if we're doing oil production, we may see lost production volumes. Well, we won't see it. That's the problem. There may be lost production volumes, and because they may be small droplets that are being lost to the system, but many droplets make a puddle or make a large volume, and so introduce errors into our production volumes. And the sticking also causes some difficulties reading oil-water interfaces for volumetric data. So you may need to consider replacing crude oil where necessary. So you use the crude oil in the very vital stages where crude oil is needed, but in the measurement process itself, you may need to replace that oil for a laboratory oil to make measurements easier to read. So just to finish off, last couple of minutes or few minutes, 3 case studies. One is this unconsolidated sand. So this was from, I think it was either Indonesia or Malaysia. I had been consulted on trying to trip out rates, and we provided trip out rates. The core came to surface like this, the oil leg, which it was about 1,000 centipoise oil with a low GOR, less than 40 scuffs per barrel GOR. The oil leg came to surface like this, completely fractured. But the water leg was perfect. And we were initially questioned about our techniques for calculating this. But what we found when we actually looked at the rates pulled to surface was the well site geologist ignored our rates, they decided, well, there's no real gas content in this oil. It's heavy oil, so we don't need to consider slow rates bringing to surface. But this is the impact of that. Fractured core, which could not be used. Then at well site, rather than doing short lengths, they did long 30-meter lengths of core, and they were trying to do foam injection from one end of the core to the other end with foam injection. And so foam was expanding, and just because it was already fractured, was pushing those fractures even further apart. That's the process. We had done CFD modeling. The well site geologist chose to ignore our recommendations. The small gas volume expanded and shattered the core, and then the fractures were further extended by foam or improper foam injection process. So optimize tripping rates and make sure everybody understands why. And actually, there's no way we could ensure that the well site geologists actually followed it, but they need to understand why they need to follow this. So the second one, that's foam injection. Make sure you've got expansion points along the core. So this is about stabilization, this second case study. So this was a field across 2 license blocks. The data was performed by the same lab, and the lab had exactly the same process for both sides of this license block. They had a well in one side and a well from another side with different operators. And the only difference between the 2 different operators is one went with the recommendation to stabilize the core, and the other operator decided they didn't want to stabilize the core. So, and the core, there were then slumping issues. So the core that wasn't stabilized had slumped. That's the sand beginning to just fall apart. And so there were 4 porosity units difference between the slumped core and the stabilized core. So always stabilize unconsolidated core. It achieves better core to log matches. And then this was the third case study, was one where the core had been frozen and then was undergoing miscible injection process. And that miscible injection was toluene and methanol, and the samples that had been frozen, so there were some totally unconsolidated portions, there were some friable or poorly consolidated sections, and there were some sections that were quite well consolidated. It's a very heterogeneous reservoir, this one. And the poorly consolidated and the well consolidated didn't go through freezing. They didn't need to go through freezing, but the unconsolidated sections were frozen. And after cleaning, when these frozen core plugs, and I still don't know the chemistry of what was actually happening, but these frozen core plugs with the liquid nitrogen, then toluene and methanol, somehow created almost like a cement of the core itself. So once the cleaning and drying had completed, these core samples looked like cement rather than unconsolidated sand. And so the cleaning process had altered the nature of these cores. So it's always recommended to do a cleaning study to look at the impact of cleaning on the core, look at the impact on the clays, look at the impact on organic material, because quite often the organic material vitamins in there may be holding the grains together, and we don't want to remove material that is holding the grains together. So we need to consider very carefully what the best cleaning technique might be for our core. So in conclusions, high quality core analysis, it starts before core analysis. It starts before coring when we're considering our process and our planning. High quality core analysis requires non-standard approaches. It's important to understand our objectives. It's important to plan our coring and our handling, and to ensure that everybody understands those objectives and the non-standard methods that are being used and why they're being used. And we need to mitigate potential damage by controlled trip outs and controlled handling procedures. And then we need to do rigorous pre-studies or pre-calculations to determine what might be appropriate and for specific methods, and consider the impact on experimental measurements and procedural adjustment where necessary. And this is just the start. Core analysis requires continual quality control throughout the whole program. And if in doubt, seek expert help. So thank you for the attention, and we will open up to any questions. So there's a couple of questions have already come in. Jules, would you recommend high-tech bulk volume measurement such as a volume scanner instead of mercury immersion? Is there any disadvantage? Yes, I would recommend those. If you have time and the cost for acquiring those. The last time I looked into laser scanners, which was approximately, or some other form of, say, 3D scanning tool, mercury immersion and the pore volume injection measurements take maybe, well, mercury immersion is maybe a few seconds. It's 1 or 2 minutes at most. The pore volume injection is somewhere between 5 to 15 minutes. With these laser scanners, the last time I looked at it was still about 30 minutes per sample to get to the same level of accuracy as, say, mercury injection, or sorry, mercury immersion. Or so yes, consider it, but you need to consider the time it's going to take to do this. So it might be okay for scal. It's possibly not going to be accepted for routine measurements because it's too time consuming and too expensive. But they can be very useful and very good. Do you recommend to slow down the trip out or the pull out of hole, say at certain pressures for gas expansion, or simply by depth? Any best practice consideration for determining the rate for pulling the core? So I mentioned, thanks Mohammed for the question. I mentioned that the way I consider that is to model the process. So model the core, model the pull out of hole from the mud system. The mud system is what you use to calculate what the outside pressure or the ambient pressure is going to be for a particular depth as you pull to surface. And so you can calculate the pressure outside the core. If you know the gas volumes and the gas content, you can calculate the rate and how much that gas is going to expand once you reach the saturation pressure. The saturation pressure is where you begin to evolve gas from that oil system. So that's the way to do it. Calculate when that will occur, pull to that depth, and then begin to slow down as the gas begins to expand. Camden has asked, what do you suggest for plugging from unconsolidated sand, which has a clay content of 40%? Is nitrogen plugging the only option? If yes, what about the quality of core analysis on those plugs with high clay content? That's a very good question, Camden. With high clay content, you will expect a fairly high water content associated with the clays. Freezing that water will disrupt the clays. So if if you can, you don't want to use freezing where possible. Now, there are other questions here. So is this a gas reservoir? Is it an oil reservoir? So there are things that can be done. So I mentioned some of the hydrocarbon stabilizing materials with low melting points. Depending on whether it's oil or gas, so if it's a gas reservoir, thank you for stating that, Camden. If it's a gas reservoir, this is very good for using something called tert butyl alcohol, or TBA. TBA has a boiling point, I think around just over 30 degrees. Oh, sorry, not a boiling point, a melting point around 30 degrees. So at standard room conditions of say 20 to 25 degrees, it is solid. But at 32 degrees or thereabouts, it begins to melt. So it becomes liquid. So you can heat this TBA, and you can pour it in around the core. And because it's an alcohol, it's miscible with water. And so it will be pulled as a liquid into the core. It will displace the gas from that core, but it will be pulled into the core. And then as it cools down, it will solidify, because it's not, water only, the problem with water is because it's this unique molecule where its density is actually higher as a solid than its densest point at 4 degrees. So when TBA or other molecules freeze and solidify, they don't have this crystallization behavior of an expanding behavior. And so it's not going to cause a problem as it solidifies. And then it holds the core together, and you can use that. If you want some more information on that, get in contact with me. But my mail address is here. And we can discuss that and how we might be able to help. Ugur has said, regarding nitrogen plugging and freezing, do you think it will change and destroy the plugs? Yeah, so I've just answered that in the previous as part of the previous question. The lower the water saturation of the core and the lower the clay content of the core, the more the more chance you might succeed with freezing. Freezing really ought to be a last option, only if you have no other ways of trying to stabilize and hold the core together. So there are potential other options before freezing. TBA is one of those if it's a gas reservoir. So consider approaches, and it depends on things like budget and time, etc. So because these are non-standard, they're not routine approaches, it's not going to be a routine to do on many samples. So it would be more special core analysis and may have higher cost involved. So it depends on things like budget and time. But for a gas reservoir, I think the previous answer to Kandan also answers yours. TBA. Khaled says saturation monitoring by attenuation of X-rays. This system can be used to measure steady state or unsteady state permeability, oil, water, and oil gas. Yes, correct. What do you recommend for gas condensate reservoir, steady state or unsteady state? I tend to recommend steady state, particularly for more permeable systems. Unsteady state is more prone to heterogeneities, and the high permeable samples, particularly for heavy oils, with a high viscosity or a mobility ratio between the fluids, it exaggerates or over exaggerates the heterogeneities in the system. And an unsteady state is more prone to error from heterogeneities than steady state. So I tend to suggest steady state. Actually, mentioning in situ monitoring is another potential process of determining porosity. So it can determine saturation, it's what it's mainly used for, but it can also help in understanding porosity. So if you have uncertainty, but again, it's a scale measurement, so it's going to, and it's expensive because you're using expensive equipment for the test. Peter says, another very interesting presentation. Many thanks, Jules. Okay, no question. Thank you, Peter. Pedro, hi Jules, on unconsolidated sands, in which grains are supported by heavy oil do I recommend running MICP on fresh rock? If it's a gas reservoir, then what you will obtain from MIC is the gas-filled pore size distribution. So it may be possible to do it on fresh rock. The problem is the start of that, you have to pull a vacuum normally on the auto pour system, which you can use on cuttings or small pieces of material or offcuts of a sample. And the pulling of the vacuum in that process could cause issues of because it may take a long time to evaporate because you've got fluids evaporating, sorry, a long time to pull the vacuum because you'll have fluids continually evaporating from the process. And so that may impact. To do MICP on that fresh rock, you may need to go back to the old style mercury injection into a standard, say 1.5 or 1 inch core plug in a core holder system. Where generally there is no vacuum pulled really at the start, or you start considering just a time aspect and not waiting for stability during the vacuum process. But it can introduce some uncertainties. But yes, you would need to modify or consider how you're going to perform that test, but it is possible. Ugo also asks, would you expect a big porosity difference between helium expansion and mercury intrusion? And for unconsolidated gas-bearing shaly sandstone. And I think the shaly portion there is very pertinent. In mercury intrusion or mercury injection, the difference between a helium system and a mercury system is usually increased by presence of clays. And so in a shaly sandstone, the clays will impact the mercury to helium correlation. The mercury, being a big molecule, can't push into some of those shaly regions. The helium is one of the, well, not the smallest, but second smallest molecule, can access those smaller pore spaces. So the helium pore volume tends to be more accurate than a mercury pore volume, but you do need to do the correlation and look at both, measure both on the same sample, and determine mercury saturation really based on the helium pore volume. How are we doing for time? Just a couple of minutes past at the moment. Derek says, what's your take on pressurized core for unconsolidated reservoirs as opposed to conventional coring? So really the only difference between pressurized core and a conventional core is the sealing of the barrel to bring it to surface. Once it's contained in the barrel, it will be filled with fluids. The mud system that is being used And so that may stabilize the core a little. I haven't had a lot of experience with this, but this is just me thinking about what's actually happening in that process. So that barrel will be filled, depending on how much the fluid is and the weights and everything. There's the potential it could stabilize the core, but there may still be some movement. But the pressurized coring may be quite useful. What you then need to consider is the process of depressurizing and how that's going to impact the core, and ensuring that that's in a controlled manner that is not going to overly affect the system. Pedro says, thanks, great presentation. Thank you, Pedro. Casey says, to get accurate saturation measurement, can the heavy oil be completely cleaned in the lab for accurate SW and porosity measurements? Yes, it's possible. The question you need to ask is, how much do I need to clean before I start, before it just becomes a pile of sand? So you do need to be careful. Generally, particularly because if these are so high permeability, and in that also then the amount of clays present may impact on the measurement, but quite often the water extraction is a relatively quick process. So it could be done in a day or less, maybe, to extract the water portion. Then you need to consider how much additional cleaning is needed to remove remaining hydrocarbons. So again, I would suggest doing a cleaning study to look at if it's a new reservoir, or you don't have any experience of how cleaning impacts the core. A cleaning study initially to see what's going to be the best approach will help in those. And then City says, could you elaborate a bit on the specialized plugging system? How is it conducted in the lab? So the specialized plugging, there are a few labs have a system that basically it's similar to the way coring works in the field. So you have an inner barrel which is static, and an outer barrel which is turning with the cutting bit on the end, and the cutting bit cuts through the rock or the core, and allows the core to push up. As you pushing down, the core then is pushed into this static inner barrel. What you can do with that static inner barrel is to line the surfaces with say a Teflon tape, so it's pre-lined and pre-ready for mounting and encapsulating the core. That's how they work. There are not many companies that use it. Most companies would either go for the liquid nitrogen freezing, or for a plunge cutting, or for the milling technique, again, which usually requires the core to be frozen or solidified in some way. Okay, that's all the questions. I want to thank everybody for attention. I'll hand back over to Jennifer, who will just finish off with some messages. Thank you, everyone. I hope the end of the year is good for you, and all the best for next year.
Thank you, Jules, and thank you, everybody. I know we ran over there slightly, but it was great. Lots of good and interesting questions for Jules. If you do have any additional questions or queries, just feel free to get in touch as well, and we will follow up with you after session. So just a quick look forward to what we have coming up for you. You'll see Justin Green is back next week on the 10th of December. He'll be bringing us the last 2020 session in our other formation damage series, microbial inhibition and prevention. all the registration details for this one will be available on our Premier Corex LinkedIn and social pages later today. So keep an eye out for them. While you're there, it'd be great if you could maybe give us a quick follow as well. We appreciate the support, and you can keep up to date on what we have coming up in 2021. And as you'll see, Jules will be back in January. Exact date will be confirmed shortly, but this one he'll be providing some more insights and laboratory learnings for water alternating gas. So yeah, keep a look on our social pages for the exact details and dates coming soon. If you've got any suggestions for upcoming schedules or topics for next year you'd like us to explore, either at public sessions or hosting specifically for your company, feel free to let us know, and we can look into these and provide some support for you there. I think that is all from us today. Thank you everyone for joining us today, and to those that have been with us over the months and series. This year has been a bit different for everyone, but as Jules said, it's been great as it's allowed us to bring these sessions to you, which we have really enjoyed, and it's been really appreciated as well hearing your feedback. So thank you for your time, and yeah, we look forward to bringing you more and seeing you next year. Thanks everyone.